Good morning, everyone. As part of my Emertxe internship, our project name is EV ADAS Dashboard, which stands for Electric Vehicle Advanced Driver Assistance System Dashboard. This project simulates a smart electric vehicles using STM32 Bluepill microcontroller, Pixim Lab simulator, and a Python dashboard. And the main objective is to monitor the vehicle performance and safety features in the real time. And then coming to the problem and solution, the problem is that modern electric vehicles generate a huge amount of sensor data. For example, vehicle speed, battery SOC, motor temperature, torque, etc. And ADAS system continuously monitor collision detection, blind spot detection. This may result in missed collision warnings, blind spot accidents, battery fails. Our solution is that we develop the EV ADAS dashboard, which provides live speed monitoring, battery monitoring, collision detection, blind spot detection, fault detection, and live Python dashboard and 4 alarm systems too. And these are all displayed in one dashboard in real time. And then coming to the next system architecture overview. In this we classified into 4 steps. First is sensor. Sensor collects the data. We simulate sensors using the potentiometers that represents acceleration pedal, brake pedal, motor temperature, battery SOC. And then step 2, the sensor values are given to the STM32 Bluepill. It performs EV calculations, ADAS processing, fault detection. Step 3 is of UART serial communication using 115222 baud rate. Coming to step 4, Python receives this data and it displays battery rate, speedometer, IV alerts. And then real world versus our project. In industry we use of pressure sensors, speed sensors, proximity sensors, and then CAN bus communication, then vehicle display, HMI display, multi-tone buses. But in our project we are not implementing it on real vehicles, so we use potentiometers, Pixim Lab simulator, STM32 Bluepill, UART communication, Python dashboard, and alarms of 4 advisories. We consisting of 9 phases of a project. Coming to the first phase, dev environment, installing the STM32 Cube IDE, Python dashboard, Pixim Lab, and then GPIO peripherals, LED, PWM, and then interrupts. Then coming to ADC sensor inputs, we have to take potentiometers, acceleration, brake, etc. EV dynamics model that measures speed, torque, SOC, etc. And then ultrasonic ADAS, left, right, front, and then time to collision, forward back collision. Fault and alarm system, it produce advisory alerts, critical alerts, etc. And UART is for communication. Then it displays on Python dashboard. We'll discuss briefly about this all phases. Coming to first sign, second phase, environment setup and GPIO peripherals. First phase, we must install all the installations what we need. Then GPIO peripherals, stage 3 and 4, ADC dashboard, ultrasonic sensor, which are TTC, FCW front, back, and front, left and right. Then time to collision, blind spot detection, parking assistance, etc. And overspeed advisory also we will be measuring, and it will be of selected limited conditions. Then fault detection alarms, it will give 4 advisories, that normal, advisory, warning, and critical. We must give conditions for that cases to work out on it. None for normal, and then advisory for such limit of threshold, then warning, then critical, and LEDs may blink by this alarm priority system. Then coming to the UART, it is of UART is for serial communication, and this includes first frame, 2 frames. First frame is for EV data, second frame is for ADAS data such as speed, SOC torque for first frame, then front distance, left distance, right distance, time to collision, alarm, blind spot. This all for the second frame. And then UART shell is mainly for testing. Instead of changing sensors physically, we send commands through serial monitor. The commands include speed, SOC, temperature, mode, reset, status, fault. Testing will be much easier. Then again, coming to the phase 9 Python dashboard, it refreshes every 100 milliseconds. It displays speedometer, battery, SOC, and then EV metrics, bird eye view, alarm status, and again that's it. Then coming to the workflow, after this workflow, overall project workflow, what we have done in the previous slides of all that. And then results and demo. The project successfully achieved real-time speed monitoring, battery tracking, collision detection, blind spot detection, fault detection, live Python dashboard, then UART shell testing, and etc. And thank you for listening. This is our STM32 project demo, and where we can see our project files. This is an EV dashboard file created separately, and in that only we have created separate source files, header files such as fault, ultrasonic sensor, ADAS, and etc. what we include in our project. And this is a main.c file where we can generate our code by pin configurations, by using pin configuration and pinning that in clock configuration also. Then it's coming to the pin configuration. We have to pin the pins which we need in our project, and how the output needs to come. We have to pin the each pin according to our need, and we have to set the timers, what we need, timer 1, timer 2, timer 3. Then coming to the UART, that's serial communication. Then coming to the clock configuration, we need to set the clock configuration in such a way that we use a multiplexers for this to configure the clock with a given frequency, what we actually need. And again, coming to the STM32, while this pin configuration and clock configuration has done, in main.c file it automatically generates the code, and you have to do some editings based on our needs. And for this we have to build a project, and after building we come to know 0 errors. Then coming to the PICSIM lab, where we use STM32F103C86 microcontroller, the board of blue pill, and we have to set a frequency, and we have to load the binary files into the PICSIM lab. And in this project we need to use square parts as potentiometers and 3 ultrasonic sensor, left, right, and mid, front. Then virtual terminal to accept the values, parameters, and LEDs for alarms, and then alarm buzzer. Then we need to change the values, and we need to check in our virtual terminal what it is happening and why the light was blinking. So when we change our values, automatically in virtual terminal the values will changes, and we will come across to know that acceleration, brake pedal, such as. And again, coming to the main.c file, we need to do some changes in that. And coming to the 01 for motor over temperature, 02 for battery, 03 for collision. So it appears like that in the time to collision. Then we need to make the ultrasonic distance 30 centimeters low. 30 centimeters low. 30 centimeters distance. Then we need to observe again in the virtual terminal what's the values have been recording or measuring. We need to compare, and we need to check every parameter by changing its values of acceleration, speed, and etc. And coming to the virtual serial port, we need to connect the comps to that port. Then in we need to configure In comport also we know the values of what we are measuring in Pixim lab. Same measurements will be done in a virtual serial port. We are able to see that all values. And coming to the command prompt, where we need to set the path of our project where it has been saved, and then we have to give our port path to. Then we need to link up with the Python dashboard, and then this is a dashboard, EV ADAS Dashboard, which is of left right side there was a bird eye view. There is a front vehicle, EV is our vehicle, and side will be of left and right. And this is EV parameters. Then this is EV parameters which we measure acceleration, brake, and that is a speed graph, what it happens. And then by changing these values, there will be a certain change in our dashboard too. We need to observe that changes. It takes few minutes of time. It's not working out. So we need to know that when the left distance, right distance, it becomes very low, it gives alarms that advisory critical, and that the distance of side vehicles is less than 30 centimeters, and it gives the alarm as advisory. When it is more 20 centimeters less, it gives us critical alarm. Then it gives time to collision rate also when the vehicle is very close to collision. And this is our EV ADAS dashboard, which was done virtual. And I thank Emertxe internship by providing this internship for many students. I hope I learned many basics, and I thank our